Hello, welcome to the next talk in this pattern recognition course. Very briefly, let us recall what we have been doing. We have been considering ways to implement the Bayes classifier. Specifically, we need to estimate the class conditional densities for implementing the Bayes classifier. So, we have been looking at various techniques for estimating class conditional densities given IID samples from a density. We want to estimate densities. Currently, we are considering the parametric way of estimating density. That means, we assume the density is known, but for values of some parameters, and we were looking at techniques for estimating the parameters. We have considered earlier the maximum likelihood estimation for parameters of a density. We have seen many examples of how it is done, and we have seen that in many cases we can actually obtain closed form solutions. It's a very efficient technique. Then in the last class, we briefly looked at another parametric way of estimating densities, what's called the Bayesian estimation of parameters. So, this class will consider Bayesian estimation more detail. We will look at a few examples. So, both this class and part of next class will be looking at Bayesian estimation. We discussed Bayesian estimation last class, but let us briefly recall the basic idea of Bayesian estimation. In the maximum likelihood case, the parameters are unknown, but are assumed constant. In the Bayesian estimation, we think of the parameter itself as a random variable. What does that give us? It allows us to capture our knowledge or lack of knowledge. See, we do not know the parameter, that is what our lack of knowledge is, but it may not be completely unknown. At least, for example, we know what space the parameter belongs to, but we are certain about the actual value of the parameter. So, this lack of knowledge or whatever partial knowledge we have about the value of a parameter is captured through a probability density over the parameter space. As I said last class, we call this the prior density of the parameter. It is prior to seeing any data. So, before we do any experiments, our whatever ideas we have about the parameter are captured in this prior density. Any information we have about the value of the parameter can be incorporated into the prior density. Okay. Then we look at the estimation process slightly differently. The data itself is now used to transform our prior density into what is called a posterior density of the parameter. Posterior is posterior to seeing the data. So, the data essentially transforms our prior density to a posterior density using Bayes theorem. Okay. This is the basic idea of the Bayesian estimation. We will see examples this class. So, to get our notation right, as earlier, unless we have some other symbol for the parameter, for generic parameters we use the symbol theta, and script d is the data that we have. So, d is simply x1, x2, xn, where xi's are IID realizations of the density. That is, we have an underlying density model f x given theta, which is known but for the values of theta. So, each of these xi's have the same density f x i given theta, and they are independent. Okay. This is the data we have, and this f is the assumed probabilistic model for the density, and we want the value of the theta. So, because we decided that the parameter itself is to be treated as a random variable, let f theta denote the prior density of the parameter, and let f theta given d be the posterior density. Just one caution about notation. Just to keep notation simple, we use f for densities of all random variables. When I want density of theta, I write it as f of theta. When I want density of x, I am writing f of x. So, in that sense, the symbol f is not specifying any specific function. Normally, in the probability literature, the random variable to which the density reverts to is put as a subscript on the density. So, for example, when I am talking about the density of f, I should say f subscript x of xi. When I am talking about the density of theta, I should say f subscript theta of at an argument value theta, and so on. It just clutters up the notation a little bit more. So, just using this unspecified f as a density function for all random variables that we are considering, the meaning will be clear from context, and all of you should be a little cautious about this notation. Okay. So, once again f theta is the prior density of the parameter and f theta given d is the posterior density. Okay. So, the Bayes theorem tells us how we can link the prior density to the posterior density. So, the posterior density f theta given d is given by f d given theta into f theta by a normalizing constant, where f d given theta because d consists of n x I, each of them are I I d, is simply product of the individual marginal density value. So, f x I given theta, which is nothing but the data likelihood that we have already seen. Okay. We also talked briefly about what are called conjugate priors last class. A form for the prior density that results in the same form for the posterior density is called a conjugate prior. Okay. So, the prior for example is normal, then we want posterior also to be normal, then the prior is conjugate. So, for a particular problem, if I choose the right form for the prior density, then the posterior may also become a density of the same class. Such a prior is called a conjugate prior. See, posterior density of course depends on the product of the prior and the data likelihood, and the form of data likelihood depends on the form of the assumed f x given theta, the density that we are estimating. So, ultimately what will be a conjugate prior is determined by the form of f x given theta that we use and hence that of the data likelihood. Okay. We will see examples later on. The reason why we want to use conjugate prior is that the prior and posterior would belong to the same class of densities, and hence calculating the posterior would be like updating parameter values. What we mean is, in this expression, if I know f theta, let us say f theta is normal with some mean and variance, and for this problem the f d given theta is of the form that when multiplied with f theta what I get is another normal density, then f theta given d also will be a normal. So, to transform f theta to f theta given d, I have to only know what will be the new mean and variance. So, in that sense, because if the prior and posterior belong to the same family of densities, transforming prior to posterior is just a parameter update step. Okay. Hence, calculating the posterior would be like updating parameter values. We are going to consider examples. One final point, how do we use the final posterior density for implementing the classifier? This is also what we discussed last time, is worth recalling again. As I said last time, there are many possibilities for this. Ultimately, we need class conditional densities for implementing Bayes classifier, that is what we are doing. So, one method is, given the posterior density, can we find a density for x based on the data, so that density is not dependent on any unknown parameter. Last class we have seen how it can be done. If I know f theta given d, we can write a density of x given data, that is density of x conditioned on the data, as the marginal of the joint x comma theta conditioned on d by integrating with respect to theta. Now, this marginal can be split into f of x given theta comma d and f theta comma d, and given theta x density of x does not depend on the data. So, this integral becomes product of f x given theta f theta given d d theta. F x given theta is the assumed density model, f theta given d the posterior that we have estimated. So, we can use this integral to find f x given d, which we can then use as the class conditional density. So, depending on the form of the posterior, we may be able to get a closed form expression for this density, and then we can use that as the class conditional density. We will see examples of how to calculate this class. There are also other possibilities. We can use one particular value of theta based on the posterior. We can, for example, take mode, that the value at which the density at the highest value. When we do that, it is called a map estimate, as I said last time, maximum posterior probability estimate, or we can take the mean of the posterior density. Both these are also often used, and we will see that in examples in this class. Okay. With that introduction, let us move on to examples. Let us first consider a very simple example. We want to estimate the mean of a Gaussian density, but this time we assume even variance is known. So, only mean is unknown. So, we have IID samples from a Gaussian density whose variance is known, and the only unknown parameter is the mean. So, with that assumption, what will be my assumed probability model? F x given theta now becomes theta is the mu, the mean of the Gaussian density, is a one dimensional example. So, f x given mu, this is the standard Gaussian density model. Okay. Once again I emphasize, in this model we are assuming sigma is known and mu is the unknown parameter which we want to estimate. Okay. We have of course as usual x1 to xn IID data from this density for estimation. So, what is the likelihood? likelihood is simply product of f xi given mu. So, that becomes just put x as xi in this expression and then take n-fold product. If I take n-fold product, I will get this term to the power n, because this does not depend on x. And here when I take the product, all of them get added up inside the exponent, right. So, my likelihood become this first term to the power n exponential sum over I xi minus mu whole square. Okay. Now, we are asking if this is the form of likelihood, what prior would be conjugate. For that, this likelihood when viewed as a function of mu, what is its main characteristic? Is as a function of mu, it has an exponential of a quadratic in mu. What is inside the exponent is some quadratic function mu. Remember that xi is a given data, they are known, they are not the variable is mu here. So, inside exponential, what I have is a quadratic in mu. So, as a function of mu, this is an exponential of a quadratic in mu. What is the density of an exponential quadratic in mu? A normal density, right. So, if the prior is normal, a normal density is exponential of quadratic, right. Then, if the prior density over mu is also normal, then what happens is I am multiplying one exponential which has a quadratic in mu with another exponential that is a quadratic in mu, because inside the exponents thing get added up, I once again get an expression which is exponential of a quadratic in mu, and that means my product would also be a normal density again, which means for this problem, that is the problem of estimating mean of a one dimensional Gaussian with variance known, the conjugate prior is a normal density. Okay. So, let us take the prior. Prior is a density on mu. Remember, we are thinking of mu itself as a random variable. So, prior is a density on the variable mu. So, we are assuming it to be normal, we will use the script n to denote normal. The notation is n of mu 0 sigma 0 is a normal density whose mean is mu 0 and whose variance is sigma 0. So, we are thinking that the prior density is normal, we are not thinking, we are taking the prior density to be normal with mean mu 0 and variance sigma 0. Okay. Now, we can calculate the posterior. The posterior of mu given d is f d given mu, this is my likelihood, into f mu, that is my prior, which is assumed to be normal with mean mu 0 and variance sigma 0, square. This is of course a normalizing constant. So, this is how I can calculate the posterior. So, I have to just substitute. So, if I substitute f of d given mu, we have from the previous slide, right, that is f of d given mu. So, I am skipping all the unnecessary constants, we only want the expression that depend on mu. So, that is why I put a proportionality sign, there is a unspecified constant. So, the posterior depends on the product of these two, and the first term f d given mu is this exponential minus 1 by 2 sigma square sum of xi minus mu whole square, and f mu is a normal with mean mu 0 and variance sigma 0 square. So, that will add 1 by 2 sigma 0 square mu minus mu 0 whole square. This is the only part of this product that depends on mu. The bottom, the denominator in this expression is an integral with mu as the dummy variable, is not dependent on mu, it is just some normalizing constant. Similarly, both these densities have some constant that do not depend on mu. So, all those are subsumed in a constant that comes here. So, that is why I put a proportionality sign instead of equal to. So, the posterior is proportional to this expression. Okay. So, let us look a little more at this expression. So, posterior is proportional to minus 1 by 2 sigma square sum I is equal to 1 to n xi minus mu whole square minus 1 by 2 sigma 0 square mu minus mu 0 whole square. So, if I expand this and write it in a quadratic, I can think that this is proportional to exponential minus half, let us take the minus half factor out into some expression a. What will be the expression a? What will come out of this? 1 by sigma square, and when I expand this I get xi square, mu square and 2 xi mu. So, one term is 1 by sigma square xi square, then the mu square term comes out, I got a sum or I is equal to 1 to n of a constant 1, that will give me n. So, I will get n by sigma square into mu square, another mu square term will come from here and that will have factor 1 by sigma 0 square. So, I will get mu square into 1 by sigma 0 square plus n by sigma square. What are the leftover terms? Minus 2 mu terms. Minus 2 mu here has coefficient summation xi by sigma square. The half is already been taken care here, right. We are only looking at A. So, the 2 mu term from here I will get summation xi by sigma square. The 2 mu term here will give me mu 0 by sigma 0 square, that is the 2 mu term. So, finally, the posterior density is proportional to exponential minus half A, where A is a quadratic in mu given by this. Okay. So, what does this tell us? Because f mu given d is proportional to exponential of quadratic in mu, as expected, the posterior is also a Gaussian density. Okay. Now, I have to figure out for this Gaussian density what is the mean and variance. Okay. Then I have completely characterized the posterior density. Because I know that the posterior density is Gaussian, let us assume that posterior density is Gaussian with mean mu n and variance sigma n square. Okay. Then the form of the posterior density would be exponential, forgetting about the constants, will be exponential minus half mu minus mu n whole square by sigma n square, that is mu square by sigma n square, mu n square by sigma n square minus 2 mu n by sigma n square. So, this will be the quadratic inside the exponent if the posterior is normal with mean mu n and variance sigma square n. We know what is the actual quadratic in the posterior. This is the actual quadratic in the posterior. So, if I want to find what is the mu n and sigma n, I have to just compare the terms, right, between that quadratic and this quadratic. So, comparing terms, we get the following. So, first, what is the coefficient of mu square here? 1 by sigma square n. What is the coefficient of mu square here? 1 by sigma 0 square plus n by sigma square, right. So, I get 1 by sigma square n is 1 by sigma 0 square plus n by sigma square. Similarly, if I take the coefficient of 2 mu, that is mu n by sigma square n. Okay. What is the coefficient of 2 mu we got earlier? Is 1 by sigma square summation xi plus mu 0 by sigma 0 square. So, right. So, by comparing coefficients, we get these equations where the unknowns are sigma square n and mu n, right. That is what we want to find. We want to find what is the posterior density. We can easily solve them. For example, from this expression, I get 1 by sigma square n is sigma square plus n sigma 0 square by sigma 0 square. Now, you invert it, you get sigma square n. So, that is sigma square n. Sigma 0 square by sigma square plus n sigma 0 square. Similarly, now substituting that sigma square n in this expression, I can calculate mu n and that turns out to be this expression. This expression is very interesting. So, I can write that expression as n sigma 0 square by n sigma 0 square plus sigma square into mu n bar plus sigma square by n sigma 0 square plus sigma square into mu n into mu 0, where mu n bar is just a symbol for this 1 by n some I is equal to 1 to n xi. I just taken this expression out. The reason for giving a symbol for this is the ML estimate, right. So, the final posterior density is Gaussian with mean mu n and variance sigma square n, okay, and these completely specify the posterior density, because posterior density is Gaussian, mean and variance completely specified. Just a word about why we chose this notation. So, we think of mu n and sigma n is the posterior density after we have seen n examples. In that sense, mu 0 sigma 0 or the density when we seen no examples, that is the prior, right. So, because mu 0 sigma 0 is for prior, mu n sigma n is the parameters of the posterior Gaussian after we see an example. Now, let us take a look at this mu n and the expressions for mu n square and sigma n square to see some interesting structure there. So, this is what we derived as our final posterior density. Posterior density is Gaussian with mean mu n and variance sigma square n, which are given by this. In this, mu 0 sigma 0 are what we have chosen. Those are the prior densities that we have started with. n is the number of examples, sigma or sigma square is the variance of the Gaussian from which data is come, which is assumed known, where we are estimating the mean of a Gaussian whose variance is known. So, sigma square is known, and mu n bar is simply an expression for 1 by n summation xi, which happens to be the ML estimate for mu in the same problem. Okay. So, thus mu n is a convex combination. I hope you can see that if it's some constant into mu n bar plus some other constant to mu 0, both the constants are positive and they add up to 1. So, mu n is a convex combination of mu n bar and mu 0. Mu n bar is nothing sample mean, is the ML estimate, which is the sample mean. So, if we did not do anything else, all this Bayesian thing, we could have simply taken sample mean as the estimate, but we are not doing that. We are taking a convex combination of the sample mean and the mean of the prior density. Mean of the prior density is what we guessed originally without seeing any data as to what the most probable or what the expected mean, expected value for the unknown mean is. So, our final estimate, the mean of the posterior density is a convex combination of mu 0, the mean of our prior density, and mu n bar, which is the sample mean, right. So, the final estimate has both the prior and the data play a role. In the ML, we are simply taking mu n bar as the final estimate. Here, we are letting our initial beliefs about the value of the unknown mu also to affect the final estimate, right. That is how this became a convex combination of the sample mean mu n bar and the prior mu 0. Second thing to notice is as n becomes large, right. Once n becomes large, n sigma 0 square, no matter what is the value of sigma 0 square is, will certainly dominate sigma square as n keeps growing large and large. So, this term becomes 1 and this term becomes 0. So, as n becomes large, the mean of the posterior will simply become the sample mean. So, if I have large data, my estimate is same as the maximum likelihood estimate, as it should be, because maximum likelihood estimate is consistent. As n tends to infinity, it will give me the right value. So, I should go there anyway, and that is also given by my posterior densities sigma goes to 0 as n tends to infinity. So, as n becomes large, sigma n becomes very small, mu n becomes same as sample mean, that means the posterior density becomes more or less a Dirac delta at the sample mean. So, that is my Bayesian estimate also, right. So, as n becomes very large, Bayesian estimate is essentially same as ML estimate as we expect. ML estimate is consistent as n tends to infinity, it gives me the true value. So, Bayesian estimate should also give us the same thing. So, as n tends to infinity, it becomes same as the ML estimate. But at any reasonable n, the actual mu n is a convex combination of mu n bar and mu 0. That means, both prior and the data have a role to play. Actually, we can see it even little more by asking, how large is large for n. So, these are our sigma square n and mu n. So, what does large n mean? Essentially, mu n becomes approximately equal to the sample mean when n sigma 0 square is much larger than sigma square. How large n should be for this to happen depends on sigma 0. If sigma 0 is small, n has to be very large to achieve this. If sigma 0 itself is large, then n does not have to be too large to achieve this. What does that mean? What does our prior say? Our prior is normal with mu 0 sigma 0. So, what we can think is, initially we think the most probable or the expected value of the unknown parameter mu is mu 0, but of course, we are not sure, and how unsure are we is determined by sigma 0. If my prior density has very small sigma 0, that means I have a lot of faith in my initial guess mu 0. On the other hand, if sigma 0 is very large, that means I do not have much faith in my initial guess mu 0. I can think of mu 0 as the initial guess and sigma 0 as the level of uncertainty in this initial guess. Take a large sigma 0 in my prior density, means I am not too sure of my guess mu 0, right. That is why the Gaussian will be very, very widely spread. If sigma 0 is small, I have a lot of confidence. So, if I have a lot of, if mu n bar becomes same as mu 0, then the convex combination will always be same. If mu 0 and sample mean happen to be the same, then obviously this whole thing will be sample mean. But on the other hand, if sample mean is much different from mu 0, then I won't believe it unless n is very large, right. That is what small sigma 0 would mean. On the other hand, if sigma 0 is large, initially itself I do not have much faith in my guess, then moderate n would be enough for me to believing only the sample mean. But in any case, if the samples are very few, then I won't let just sample mean take me astray. I have some control by what prior I choose. Of course, mu 0 sigma 0 is what we choose. So, that depends on whatever initial knowledge we have about the area in the parameter space where we think the true value of mu lies. What its utility is that if the first few data that we got by our misfortune happen to be outliers, that immediately does not take away our guess too far, our estimate too far. Okay. Now, of course, so far we know what the estimate is. We just told you, we just calculated that the posterior density is Gaussian with mean mu n and variance sigma square n, and we seen how to calculate mu n and sigma square n. Okay. So, the Bayesian estimate the whole posterior density. So, what should we take as the final estimate? As we explained earlier today, we can use mean or mode of the posterior density, because the posterior density is Gaussian, its mean and mode both are equal to its mean, and that is mu n. So, which means I can simply take mu n to be the value of the unknown mean. That means, my class conditional density, I am originally assuming it to be normal with mean mu, which is unknown, and variance sigma square, which is known. Now, my estimate could be simply mean or mode of the posterior. That means, I can simply take my class conditional density to be Gaussian with mean mu n and variance sigma square. This is one thing I can do. I can simply take the mean or mode of the posterior density at the parameter value, which happens to be mu n, and hence I will say my final class conditional density is Gaussian with mean mu n and variance sigma square, because I started with a model where sigma square is known. On the other hand, as I said, we can actually calculate a density model for the data for x based only on the data, right. So, in this particular problem, it happens to be easy to calculate, easy in a figurative sense. We are not actually calculating. The algebra involved is quite complicated. It would have taken at least 4 or 5 slides for me to show you the algebra, but let us just please write the expression. So, f x given d is integral f x given mu, f mu given d d mu, right. This were integrated this from mu, so only x and d will remain. What is f x given mu? This is my assumed model, 1 by sigma root 2 pi exponential minus x minus mu whole square by 2 sigma square, that is the first term, multiplied by second term f mu given d is normal with mean mu n and variance sigma n. So, that is 1 by sigma n root 2 pi exponential minus mu n whole square by 2 sigma square n integrated with respect to mu. So, this is my expression for f x given d. Of course, this looks a complicated integral. What I have is a quadratic in mu here, right. X survives the integration. So, there is a quadratic in mu here, mu n and sigma n are given. So, ultimately I get some constant into exponential quadratic in mu. So, you can at least see that there will be some simplifications possible by using the standard Gaussian integral. After a lot of lengthy algebra, one can actually crunch this integral and show that this turns out to be this, right. Once I do all the algebra right, that expression turns out to be this. What is this? This says f x given d is Gaussian with mean mu n and variance sigma square n plus sigma square, right. So, for example, instead of just taking mu n as which is the mean or mode of the posterior density as my estimate, I can take my class conditional density estimate to be this. That means, I will use a class conditional density which is still Gaussian with mean mu n as earlier, but now variance is sigma square plus sigma square. If I take the mean or mode of the class conditional density as my estimate, I would have taken my mean or mode of the posterior density as my estimate, then final class conditional density would have been Gaussian with mean mu n and variance sigma square, which is originally assumed known. But what our calculation f x given d shows us that the right class conditional density to use is Gaussian with mean mu n, but with variance sigma square plus sigma square n. The idea is mu n is only estimate of the unknown mean, and hence sigma square n is our initial at that level uncertainty in our estimate. So, it is better to take our class conditional density after seeing n samples as Gaussian with mean mu n and variance sigma square plus sigma square n. Once again, as n becomes larger and larger, the sigma square n becomes 0 and this becomes the ML estimate which is consistent, right. So, seamlessly as the data increases, ultimately it becomes Gaussian with sample mean as the value of the unknown parameter and variance to be sigma square. So, which means if I use this class conditional density, naturally we take care of the sample size problems. If you remember, at the end of ML, we said the main problem with ML is while it is consistent at small sample size, our estimate may not be too good. Now, here by calculating fx given d, we realize that if when I am taking mu n as my estimate, I do not simply plug mu n into the density model we assumed, which is Gaussian with mean mu and known variance sigma square. I increase the variance of the class conditional density model I use to account for my current level of uncertainty in my estimate. So, this is another very interesting thing about Bayesian estimation. It does take care of the sample size problem. Okay. So, this one example, of course, as you can see, when I derived the ML estimate, we actually taken a problem where both mean and variance of the Gaussian are unknown. We taken our first simple example as the unknown density is Gaussian and we directly estimated both unknown mean. Here just estimating the mean itself involves considerable algebra, but essentially it allows us to take prior beliefs into account, ensure that at all sample sizes we don't get led astray too easily by outliers and so on. That is what we are gaining by Bayesian estimation for the increased complexity. Right. We will see one more simple example, right. Estimating a Bernoulli density. This is the second example we took even when we did ML, maximum likelihood. So, like that here also let us consider estimating a Bernoulli density with parameter p. So, what is the Bernoulli density with parameter p? P the parameter. So, the densities of x given p is p power 1 minus p 1 x only 0 1 value. So, by density I mean it is actually a mass function, right. It has only two values f 0 given p, f 1 given p. F 0 given p is 1 minus p, f 1 given p is the Bernoulli. So, it takes value 1 with parameters with probability p and 0 with probability 1 minus p. Okay. So, what is the likelihood? Likelihood is product of this over xi, that is I is equal to 1 to n f x i. So, what is f x i? P to the power x i 1 minus p to the power 1 minus x i. So, if I do this product, I get p to the power of sum x i into 1 minus p to the power of n minus summation x i. Okay. That is my likelihood. So, the likelihood is of the form p to the power something into 1 minus p to the power something. Now, I have to multiply this likelihood with some prior and the product should once again be the same form as the prior. So, if I choose prior also to be p to the power something into 1 minus p to the power something, then the product will once again be p to the power something into 1 minus p to the power something. So, the prior that we need, right, should be some density which is proportional to p to the power of a into 1 minus p to the power b, and this should be a density because p is a continuous value. It can take any value between 0 and 1. So, it should be a well defined density over the space 0 1 and should have a form which says that the density is proportional, density is some constant times p to the power of something into 1 minus p to the power something. The reason why this should be the right prior is, if that were the prior and then I multiply with the likelihood, then what I get is p to the power something into 1 minus p to the power something. So, which means the posterior will once again be in the same class as the prior. So, the question is, what are the densities that have this form? An important density that has this form is what is called the beta density. It has two parameters a and b, and it is given by f p is gamma of a plus b by gamma of a into gamma of b into p to the power of a minus 1, 1 minus p to the power of b minus 1, the density over 0 1 and a b are constants which are assumed to be greater than or equal to 1. Okay. Where the gamma is the gamma function, okay, the gamma function is given by gamma of z is 0 to infinity x to the power z minus 1 e to the power minus x dx. I hope all of you have come across gamma function sometime. There are many places where you could have studied gamma function, including a probability course. But anyway, with this as the gamma function, this is the density. While I am assuming that all the people using this course know basic probability, which means you know about densities, joint densities, all the standard densities such as exponential, Gaussian, Bernoulli, binomial, Poisson and so on. This beta density is not something that one often comes across in first course in probability. So, we will spend a little time on understanding the beta density first. Okay. So, beta density, beta a comma b, beta density with parameters a and b is the density given by f p is gamma of a plus b by gamma a into gamma b into p to the power a minus 1 minus p to the power b minus 1. Okay. This is the density. This is a very important density over 0 1. Many other density over 0 1 all of you know, for example, uniform is one density over 0 1 that everybody knows. So, after uniform density possibly this is one of the very important continuous densities which are defined over 0 1, where the random variable takes values only over 0 1. Okay. If a is equal to b is equal to 1, if I put a is equal to 1, b is equal to 1, f p is a constant for all p belonging to 0 1, that is nothing but the uniform density. The constant should turn out to be the right constant, namely 1, but that it will currently show that this is a density. So, if a is equal to b is equal to 1, it reduces to uniform density, but if a is equal to b, if a and b are different, then it is a density which is not uniform over. So, that is how we would be able to give some bias to the give some view to our initial views about the values of p. Okay. We will come back to that again later, but just right now let us remember that a is equal to b equal to 1, it reduces to uniform density. Now, first let us show that this is the density. Okay. What do you have to show for this to be a density? Gamma function is obviously positive and p is between 0 and 1, a and b are greater than or equal to 1. So, this entire expression is positive. So, the only thing we have to show is integrated over 0 to 1 with respect to p, this expression should be 1. So, which is same as gamma of a plus b integral 0 to 1 p to the power a minus 1 minus p to the power b minus 1 dp, this should be equal to gamma a into gamma b. So, that if I bring gamma a gamma b this side, that whole thing will become 1. Okay. So, this is what I have to show that this is a density. Okay. This is a little non-trivial thing. So, let us just show it. Okay. So, first, so this is what we want to show. So, let us take the LHS gamma a into gamma b and ask what is it. So, this is the gamma function. So, because I want product of two gamma functions, I have taken different dummy variables. So, gamma a is x to the power a minus 1 e to the power minus x dx over 0 to infinity. Gamma b is y to the power b minus 1 e to the power minus 5 dy over 0 to infinity. Because I have taken different variables, I can write it as a double integral. So, 0 to infinity e to the power minus x plus 5 x to the power a minus 1 y to the power b minus 1 dy dx. I need some order of integration, it really does not matter, there are independent integrals here. So, I just chose dy and then dx. Okay. Once I do that, in the inner integral, we will make a small change of variable. So, the inner integral with respect to y. So, let us change y to t using the transformation t is equal to x plus 5. What will this mean? Dt is dy is dt. So, that does not change. When y takes value 0, t takes value x. When y takes infinity, t takes infinity. So, the limits 0 to infinity for y will become x to infinity for t, and x plus 5 will be substituted by t, and x and y itself will become t minus x. Okay. So, now this integral will now become, so x plus 5 has become t, x power a minus 1 as it is, y has become t minus x, the variable has become dt, and limits of change from x to infinity. So, this is a dt dx integral, x is the outer integral that goes from 0 to infinity, t is the inner integral that goes from x to infinity. Okay. So, let us say I want to change the order of integration, that is I want to first integrate with respect to x, then integrate with respect to t. So, how do the limits change? Here for each x, t goes from x to infinity, which means for for each t, x goes from 0 to t. Okay. So, if I change the order of integration, this expression will become the outer integral is now dt integral, right. The inner integral is dx integral. So, it becomes 0 to infinity, t goes from 0 to infinity now, and x goes from 0 to t. Earlier, x goes from 0 to infinity, t goes from x to infinity, which means for each x, t goes from x to infinity, which means very simple geometry will tell you, which means for each t, x goes from 0 to t. Okay. Now, let us start with this. So, we come up till here, gamma a, gamma b is given by this expression. Now, once again we will make a change of variable in the inner integral, right. We change x to tu, where u is the new variable. Okay. What does this give us? When x goes from 0 to t, what happens to u? When x is equal to 0, u is 0. When x is equal to 2, u is equal to 1. So, as x goes from 0 to t, u goes from 0 to 1 and dx is t du. So, using that we change the variable from x to u in the inner integral. So, that will give me, if I change from x to u, this becomes a du integral, e power minus t stays, x has become tu. So, that is t to the power of u minus 1, t to the power of a minus 1 and u to the power of a minus 1. Now, once again x has become tu, so I can take t common. So, it becomes t to the power b minus 1 into 1 minus u to the power b minus 1 and dx has become t du. Now, I can gather together all the t terms, there is a t power a minus 1 here, t power b minus 1 here and a t here. So, that gives me t power a plus b minus 1, because 1 minus 1 will cancel with this t. So, that will give me this 0 to infinity, 0 to t, e power minus t, t to the power of a plus b minus 1, then u to the power of a minus 1, 1 minus u to the power of b minus 1 du dt. Now, as you can see in this double integral, right, the limits do not depend on each other and the t and u terms are separable. So, I can write this as a product of two integrals, right. So, I bring all the t terms out, 0 to infinity e power minus t, t to the power of a plus b minus 1 dt, and all the u terms separately, 0 to 1, u to the power of a minus 1, 1 minus u to b minus 1 du. Now, are we done? Can we recognize this? A 0 to infinity e power minus t, t to the power something dt. This is nothing but a gamma function of a plus b, right. So, what have we got? This is a gamma function a plus b. So, as gamma of a plus b, 0 to 1, u to the power of a minus 1, 1 minus u to the power of b minus 1 du. So, if I take in u to be p, then this is exactly what we wanted. Gamma a gamma b is gamma of a plus b into 0 to 1, p to the power of a minus 1 into 1 minus p to the power of b minus 1 dp. So, this completes the proof that the beta density is indeed a density. Okay. There are some interesting things about the beta density. This is the beta density. Suppose I want the mode of the beta density. That means, I want the value of p at which f p is maximum. That is very simple. You differentiate this with respect to p equal to 0. Using that, one can easily calculate that the mode occurs at a minus 1 by a plus b minus 2. Okay. Once again, if a is equal to 1 and b is equal to 1, this is an undefined quantity 0 by 0. Obviously, the uniform density has no mode. Okay. Similarly, we can also find the mean value of this. How do I find the mean value of this? If I want to find mean, this is the FP density. So, I have to do P into FP dP 0 to 1. This also easy to do. So, let us do this. So, bring gamma A plus B, this constant out. So, I have 0 to 1. This P goes with P of A minus 1 to give me P of A 1 minus P of B minus 1 dP. Now, because we already shown beta density to be density, right, we know if I multiply this with, see, it is just another beta density, where in place of A I have A plus 1, in place of B I have B. So, I know this integral can be written in terms of gammas. So, that will be gamma A plus 1 gamma B by gamma A plus B plus 1, right, because if I had given 1 by this as the constant here, this would have been 1, because that is a beta density. Now, I suppose all of you know the standard property of the gamma function, which can be obtained by integrating by parts the gamma function. That is, for any x, gamma of x is x gamma gamma of x plus 1 is x gamma x. So, gamma of a plus 1 is a gamma a, and gamma of a plus b plus 1 is a plus b gamma a plus b, right. So, if I write that, it becomes gamma of a plus b by gamma b, a into gamma b, a plus b into gamma a plus b. So, cancel all the gamma terms, you get a by a plus b at the mean. So, for the beta density, a by a plus b is the mean and a minus 1 by a plus b minus 2 is the mode. Okay. So much about the beta density. Let us get back to the problem that we are interested in. The original problem was we wanted to estimate the parameter of a Bernoulli density, and we have taken the beta density to be the prior. Okay. So, what is the posterior density? So, we are doing the Bayesian estimation of the Bernoulli parameter. So, we want to calculate the posterior density. So, posterior density is given by f of p given d is f of d given p f p by some normalizing constant. So, I will just put that as k. So, f p given d is some constant k times f of d given p f p. Now, I can substitute f of d given p and f p. F p is the beta density. So, it has some constant in terms of gamma functions. This we already calculated earlier. So, forgetting about the constants, I change the constant k to k1. F of d given p was seen to be p to the power summation x I 1 minus p to the power n minus summation x I, and we have taken the prior to be beta. So, p to the power a minus 1 minus p to the power b minus 1. So, the constant that comes in beta is subsumed into this, that is why that k has been changed to k1. So, what is this k1 times? If I gather together all the p terms, I get p to the power summation x I plus a minus 1, 1 minus p to the power n plus b minus summation x I minus 1. So, this is once again a beta density. Only thing is the parameters have changed. We started with the prior, which is beta with parameters a comma b, then the posterior turns out to be beta with parameters summation x I plus a and n plus b minus summation x I. So, this is the posterior density happens to be beta. Now, once you have posterior density, we have, as we have seen earlier, we have various choices for the estimate. We can use the mean of the posterior density, we can use the mode of the posterior density, or we can actually calculate f x given d. Once again, let us do all this. Suppose we want the map estimate. What is the map estimate? Is the maximum of the posterior density, that is, we take the mode of the posterior density as our estimate. Okay. So, just now we shown that for a posterior density with parameters a and b, the mode is a minus 1 by a plus b minus 2. Okay. Here are my parameters, summation x I plus a and n plus b minus summation x I, where remember n is the number of samples we have. So, these are the parameters. So, which means my map estimate will be summation x I plus a minus 1, what was a is summation x I plus a, and what was b is when I do a plus b, what happens is my a is summation x I plus a, my b parameter is n plus b minus summation x I. So, a plus b, the summation x I will cancel. Okay. So, my map estimate will be I is equal to 1 to n summation x I plus a minus 1 by n plus a plus b minus 2. Okay. The one thing that we can immediately see in this is the following. If I take a is equal to b is equal to 1, then it becomes 1 by n summation x I, which is nothing but the sample mean. For Bernoulli also, we know the sample mean is the ML estimate. So, if I take a is equal to b is equal to 1, we get the sample estimate, no matter what n is, we get ML estimate. Why is that so? When a is equal to b is equal to 1, the prior is flat. The posterior f of d given theta, f of theta given d is given by the product of f of d given theta into f theta, the likelihood and the posterior by some normalizing constant. So, if I am maximizing the posterior and f theta is a constant, then maximizer of the posterior will be same as the maximum of the likelihood, and that is the ML estimate. So, if I take a is equal to b is equal to 1, for all n, the map estimate is same as the maximum likelihood estimate, as you would expect, because for a is equal to b equal to 1, the prior is flat. Okay. So, if a and b are different, then of course, we get a different this thing. See, this is a Bernoulli random variable. So, xi's are 0 or 1. So, we can think of n as the number of trials and each xi is either 1 or 0 depending on whether success or failure. Then ML estimate is nothing but the fraction of success. Here instead of just making the fraction of success, I have added some A's and B's, right, based on my initial belief. So, that is how my initial belief change the final estimate. We will come to that. I will explain those A's and B's in a minute, but let us continue. This is what the map estimate would have been. Now, let us ask what would be if we calculate f x given d as we did last time. Okay. Now, this is a binary, this x is a binary random variable, right. So, x takes only values 0 and 1, which means there are only basically this is a mass function and there are only two values for it, f1 given d, f0 given d. Let us write that as probability x is equal to 1 given d and probability x is equal to 0 given d. They sum to 1. So, I need only one of them, right. So, to calculate f x given d, I need to only calculate p x is equal to 1 given d. That is once again given by 0 to 1, p x is equal to 1 given p, f p given d, this is the posterior, integrate over p. Now, given our model, p is equal to p, probability x is equal to 1 given p is p and this is the posterior. So, it becomes 0 to 1 p f p given d dp, f p given d is the density over p. So, this is nothing but the mean of the posterior density. So, if I actually calculate f of x given d, that is determined by the mean of the posterior density and we already know the mean of the posterior density. This is a by a plus b. So, that is I is equal to 1 to n xi plus a by n plus a plus b. Okay. So, that is the reason why earlier slide I have only shown the example of using map estimate. I did not show the example of using the mean, because using mean or using f x given d is the same. So, if I actually want to calculate f x given d, in this case that turns out to be the mean of the posterior density, otherwise I can use the map estimate. So, let us take a look, we can discuss either of them. So, let us look at the mean. Okay. So, this turns out to be simply the mean of the posterior density. So, let us look at the ML estimate, the two estimates. This is the ML estimate, which is the sample mean, which is the fraction of success, number of success by total number of trials. This is the base estimate, I is equal to 1 to 1 x I plus a by n plus a plus b. Essentially, the Bayesian estimate's value depends on a and b, which are the prior parameters of the prior. So, our choice of prior determines the values of a and b. What does that mean? Once again, let us take this the two estimates. We already know what maximum likelihood estimate represents. The summation xi is the number of successes, because x's are 1 or 0 and n is the total trials, that is the total number of success by total number of trials. Now, I can interpret the base as follows. I can think of, so I have added some a to summation xi. So, it is like I have just added a few more successes and added a plus b to total number of trials. So, it is like I have added a plus b more trials, of which I decided a are successes, right. So, we can say before any data is seen, we already have started with a plus b fictitious trials, of which a were successes. We choose a and b to give some value for p like this. Of course, I can it is not dependent only on the fraction of a by a plus b, because the actual shape of the density depends on the individual values of a and b. But essentially, it is like saying that I am tossing a coin, I want to find the probability of heads. If I am looking only at the data, then if I toss the coin only once, then my only possible maximum likelihood estimates are either 1 or 0, which is ridiculous, right. But if I think that the coin is fair and I think that I need at least a sample size of 5, then I can take some, say, a sample size of 6, I take a is equal to b is equal to 3. Then even if I only one data, then it becomes 3 plus 1 by 3 plus 3 plus 1. Okay. So, it does not go too far away. As the number of trials increases, right, then no, summation xi will be much larger than a, n will be much larger than a plus b. So, essentially this will be same as the ML estimate. But for small sample case, it is like we started with a plus b fictitious trials, of which a were successes, right. If you remember, last class we looked at the philosophical standpoint of Bayesian approach. There I gave you the example of 3 scenarios. All of them, the data says that it is perfect. Somebody wanted to guess whether coin turns heads or tails, 3 out of 3 times he guessed correctly. In ML estimate, I have to estimate the parameter as 1, but in the Bayesian estimate, depending on my prior, right, till there is overwhelming evidence, right, a few lucky runs will not throw my estimate away. That is essentially how the prior affects my final estimate. Okay. So, this is how prior affects the final estimate. So, in both these examples, both in the normal example and in the Bernoulli example, you can see how the prior has played a role in shaping the final estimate in view of the data. Right? As a matter of fact, when I look at the mean of the posterior density, the estimate in the Bernoulli case, the role of the prior density parameters a and b is particularly clear. Okay. So, we will stop here today, and next class we will look at a couple of more examples of Bayesian estimation, and then move on to other topics. Thank you.